Yes, yes.
And I guess we already have Josh with us.
Yeah, yeah. He's backstage
Can we
awaiting
have him on
us
the
to get
screen,
over.
please? Yes. Hi,
Hey,
Josh. How
George.
are you?
Hey, great to be here, guys.
Yes, so good to see you. And what's that number? 5,000? Like, is that the cheese slicer that you have eaten?
Oh, that's something from the startup I was
Okay,
working at
that's
before.
cool. So yeah, according to the IST, it's been a very early morning, I guess, but it's pretty late for you, right?
Yeah, it's evening here, so it's a good way
Mhm.
to end a nice day.
Right, so yep.
Had
And
some
starting first of all, I want to know, I keep aside the entropy and all. I want to know what's your favorite jutsu move.
jujitsu move.
Yes.
I was at practice this morning, actually, in the afternoon. I like the triangle choke. It's
Okay,
a
that's cool.
it's a
Yes, just a
chokehold.
brief introduction about Josh. He's like one of the coolest guy that you ever found on the internet. He's probably doing like in the morning. I don't know, probably jitsu in the night. Probably is skateboarding or something. But yes, so he's doing all the extracurricular activities, all the extreme sports. As a very sporty guy, and besides that, he runs his Chaintuts and delivers exciting information to the community. And he is so knowledgeable and always be supporting community with his extreme knowledge. So here we are with us, Chaintuts and Mr. Josh itself from Microsoft, and he will be sharing his research or you can say knowledge about the entropy, which we all need to learn about. So the stage is all yours, Josh, and we are pretty
Well,
excited.
well, thank you guys so much for having me. I really love the work that you guys are doing, and it's always really cool to be a part of the community that's here. So, yeah, today we're going to talk about getting random, entropy, and its uses in cryptocurrencies. So, um, thanks for the introduction. Like you said, I'm a software engineer at Microsoft. I do sort of like back end and systems programming for my day job. And on the side, I just love sharing knowledge of computer science with people, kind of breaking down and making topics, hopefully easy to understand for non technical through computer science people. Just, giving all those little breakdowns about interesting topics in cryptography and computer science. So today we're going to talk about entropy, and why is this interesting? Why is this important to us in the blockchain space? Entropy is something that even outside of cryptocurrency is super important for all the cryptography we use day to day to secure our web browsing and secure our data stored on our hard drives encrypted at rest. And broken randomness can break cryptographic systems in really interesting ways. So we're going to talk about the different ways that we use random number generators and random functions in blockchains. And aside from some of the obvious ones, there's some interesting use cases that folks might have not thought of before. So hopefully, it's an interesting dive into why this topic is so important. So, entropy in a computer science sense is a little bit different than sort of the definition we use in physics. Physics is kind of the degree of disorder in the system. They say that, our universe is always full of entropy and unpredictability. Um, but in a computer science sense, we're talking about randomness collected by computer systems for use in things like key generation, nonces, and those kind of use cases. And there's really different sort of levels or categories of randomness for this purpose in computer science. So let's kind of talk about those. There are true random sources that can actually be captured in computer science sense for use. There's non-cryptographic pseudo-random numbers, and there are cryptographically secure pseudo-random number sources. And that's kind of what we are usually talking about when we're talking about applied cryptography. There are some sources of what we would call true randomness in the universe. And one of those sources, which I think is kind of interesting, is radioactive decay. So like certain, atoms and isotopes, I'm not a physics guy, right? But they break down in ways that are considered to be truly unpredictable in the physical universe. And this entropy actually is possible to record by computers. People have built prototypes of true random number generators that use things like radioactive decay. But the problem for computer science folks is this is generally pretty impractical, right? We can't all carry around radioactive isotopes in our phones or in our computing devices. And not only that, but these systems can also break. And if a true random source like that breaks, it breaks our random number generator. We can have predictable keys and those sorts of things. So even though this is a possible source of random numbers for computing, it's not a practical one. So instead, when we're talking about computers, we generally use what we call pseudo-randomness. So instead of relying on true physical universe sources of entropy, we rely on random algorithms instead. Now, there's kind of a problem with creating random functions, and that's the fact that, sort of opposite to, radioactive decay or something like that, computers are very, very predictable machines. We know as computer scientists and as programmers that computers do exactly what we tell them, right? They execute functions exactly. And so it's actually quite difficult to harvest randomness. But we've come up with solutions for this. And there's two sort of different broad categories of algorithms for getting random bits out of a computer. There's regular pseudo-random functions, and then there's pseudo-random functions that are considered cryptographically secure, meaning that they're usable for purposes like key generation. So I put together a little program in Python that generates a bunch of random numbers, one using a non-cryptosecure PRNG, and this very commonly used algorithm in most programming languages called the Mersenne twister. And on the right-hand side of the slide, I have numbers generated by a cryptographically secure source that's provided by the operating system. And in this Python script, that is made accessible to us through the os.urandom API. So these are histograms showing the distribution of random numbers generated out of, like, say, 100. I think I did 100,000 numbers here. What's the difference in looking at these two graphs? It's not immediately obvious. The distribution of these random numbers seems pretty even. So we have a good distribution of randomness through the non-cryptosecure source, the Mersenne twister, and we have a pretty good distribution with the cryptosecure source. Well, the answer, the difference between these two types, is the fact that it's not just about a uniform distribution of the random numbers. It's not about the fact that if you generate 100 random numbers, where they fall on the spectrum of 0 to 100. It's also about the predictability of new random bits. And what I mean by that is, if you're given a set of random numbers generated by this random function, can you use that information to predict future bits that will come out of that random function? So, for example, the very popular Mersenne twister, which is usually what you get when you use a programming language's built-in random function, Given a certain amount of random numbers generated, you can actually very reliably predict the next random numbers that will come out of that. So, even if you seed your random function with, say, the millisecond time on your computer, given 624 is actually the exact number for the twister, you can predict reliably the next numbers to come out of that function. Now, for a crypto-secure random source, no matter how many random numbers you take out of that source, you can't predict in any way what the next bits will be. And that's actually really important for key generation and that sort of thing. If we're gonna say have a server that's gonna say it's a server for Coinbase or server for some other crypto exchange or web wallet, and we're generating a bunch of keys for hundreds of thousands of users, it would be really bad if an attacker got some subset of those numbers and then could predict all of the new keys that were generated. So, again, that's very, very bad from a security perspective. So for key generation, we need to use these crypto secure sources. Now, how do these crypto secure sources actually work? They use a mechanism that I kind of like to call, as an easy way to remember, seed and feed. Again, computers are really predictable by nature, so we still need to, for our random functions, harvest some amount of random data from the environment around the machine. So we can use relatively unpredictable environmental sources. Common ones include mouse movement, like jiggling your mouse around as you go about your business on the computer. The key press timings down to millisecond or microsecond intervals. Phones use accelerometer data as part of how they feed their RNGs. You can even use things like temperature. Beyond that, for the extra paranoid, you could even feed a CSPRNG with something like dice rolls, right? Something that's physically very random, or shuffling decks of cards and feeding that into an algorithm. There are tools out there that allow you to do this for things like, creating crypto wallets or creating diceware passwords. And then what we do is, even collecting all that sort of randomness isn't generally good enough to directly generate keys. So what we do is we feed those sources to a secure cryptographic function. And examples of things that could be used for this are things like the SHA hashing algorithm, or, as is often used from my understanding, things like an AES block cipher in counter mode or some other mode that works for this source. A production example of a CSPRNG is the Fortuna RNG, and that's something that's detailed in books like Practical Cryptography, other online sources that you can read about. And the important thing is that we always get unpredictable random bits out of these functions. Our computers constantly need sources of randomness. Like every time you visit a new web page and you're doing a TLS handshake, you're generating new keys and those sorts of things. So our random functions, our operating system that exposes this API, is always taking in new sources of entropy from the environment, like your key press timings, and then using that to feed these cryptographic functions. So I made some little standalone examples. They're not like production ready, cryptographically secure things, but demonstrating these concepts. One of them is a diceware password tool, where you can roll dice and input the dice rolls, and it'll show you the entropy in bits and give you words that you can string together to create secure passwords. Another example is a entropy collector that uses an accelerometer. So it collects a bunch of data from your random movements at short intervals and feeds them to one of these cryptographically secure functions. So it's really interesting to kind of see examples of this and break down on a more macro scale how these algorithms work. So now that we have a good idea of what random functions look like, let's talk about some uses of cryptographic randomness in cryptocurrencies. There's a couple different places where we need to use randomness in order to build secure systems. The obvious one is key generation, right? Private keys are the core of crypto ownership. That's what allows us to be our own bank, so to speak, is we can hold our own keys. But they're also important for signatures, and they're important for our consensus mechanisms. Proof of work and proof of stake both use randomness at the core to secure the system. And of course, we're going to talk about what happens when these things break, which I think is the interesting part, like why it's so important that we get randomness right for these functions. Again, key generation is the first, I think, obvious use case. Private keys are the core of our crypto ownership. Your keys, your coins. Not your keys, not your coins, as we often say. And it's critically important that these keys are random. Keys themselves, for pretty much every major cryptocurrency that I know of, are 256 bits. So your Ethereum address, your Bitcoin address, your Litecoin address are backed by a private key that is 256 bits of random data. Now, there's a caveat to that somewhat, is usually seed phrases are 12 to 24 words, and a 12-word seed phrase starts with 128 bits of entropy. And that entropy is stretched using a key stretching function that turns it into, a 256-bit key. And there's a lot more that goes into the bit 39 and bit 32 and bit 44 standards that I'm not going to touch, but we're generally starting with anywhere from 128 bits up to 256 bits of entropy from a random source. That could be generated by your PC if it's a desktop wallet. It could be generated by a server if it's something like, an exchange or a web wallet. And, it could even be from a random number generator built into a hardware wallet. And the cool thing about the hardware wallets is that random source is built into a standalone device, and the keys never leave that device. I mean, all of us crypto security folks love to recommend people use those kind of offline devices because there's less of a chance of those keys being leaked or even the randomness used to generate those keys being leaked in any way. Now, you may be wondering, is 256 bits enough? Is that enough entropy to make sure nobody can ever guess my key? And the answer to that is if it is securely generated from a cryptosecure function or even something like, good dice rolls, yes. That gives us the numbers between 0 and 2 to the 256 power minus 1. And that's a really, really, really big number. I'm kind of baffled by the math, right? 2 to the 256 power is somewhere on the order of the number of atoms in the observable universe, at least what we think is. Think about how many atoms are just in your phone or your table. It's just a number that is so big that human beings can't comprehend how big that is. So what happens if the keys aren't random enough? The answer is, I think, somewhat obvious, is a key that's not random enough is pretty much the worst case scenario for a crypto user. That if your key is not strong enough and somebody can guess that key, the attacker can steal your coins. Because at the end of the day, anybody that has your seed phrase or your private keys controls those coins as much as you do. So one of you is going to move them first, either you or the attacker. And, if you have a poorly generated private key, the attacker can then take the coins, move them to an attacker-controlled wallet in a new transaction. Now, what's a practical example of this? A very good practical example of this poor key generation is what we call brain wallets. This is the idea of generating your own passphrase. So not using a secure function to generate 256 or 128 bits, but rather coming up with a password, say, desk, microphone, phone, laptop, hashing that through SHA-256, which will give you a 256-bit number, and using that as the 256-bit private key. Now, there's been a ton of research into how bad these are and how poor humans are at entropy. Ryan Castellucci, a researcher, did a phenomenal DEF CON. It's not even passphrases that seem like they would be okay. I mean, brain wallets that used long passphrases from things like movies, quotes from movies, quotes from books and different literature, have had their funds stolen. There's a whole network of attackers that do nothing but try to crack brain wallets and race to steal the coins in them. It's really important to remember human beings are bad at entropy. Even though we said computers are bad at entropy at the start, we can at least use secure algorithms through computers, but people trying to come up with randomness rarely works out very well. Another important use of entropy in cryptocurrencies is through signatures. So every transaction has to be signed by the person that controls the wallet. So if I want to send, an Ethereum donation to the RazorSec team, I would have to sign a transaction to do that donation. And these signatures, the algorithms that are used to generate these signatures, require a random nonce for every transaction. And this nonce must be one-time use. So we use SecP256K1, an elliptic curve algorithm for Bitcoin and Ethereum, and again, pretty much every major cryptocurrency that I know of, because of its efficiency and the fact that it has small keys compared to, something like RSA. But nonce reuse can easily reveal the private key. There's some sort of math that you can do. If you have two different signatures that reuse the nonce, it's actually fairly trivial to compute the private key from that. And there have been, capture the flag type activities that demonstrate this. And again, I have a small sort of standalone tool called Not OK Reuse that is a demo of this concept. So there have been instances in the past, and I don't remember the wallets off the top of my head, but where sloppy wallet programming led to nonce reuse and therefore attackers stealing funds from the users of those wallets. Now, some perhaps less obvious uses of randomness, besides just key generation or signatures, is our consensus mechanisms, our decentralized consensus mechanisms that we use to secure our blockchains. Both proof of work and proof of stake rely heavily on entropy. We have to make it difficult for an attacker to change the state of the blockchain and to sustain that attack over time. In other words, we need the block winner, the validator, or the miner that gets the block to be chosen at random, and random in a cryptographically secure sense. But at the same time, we also want to reward those that invest in more mining hardware, so hash power, or more stake for proof of stake systems with a higher probability of being selected. And there's some kind of interesting mechanisms that allow us to have both of these properties, where it's very difficult for an attacker to guess and sustain an attack on the network, but also for us to wait and sort of favor folks that invest more into the networks. Proof of work uses the pseudo-random property of cryptographic hash functions like SHA-256. So Bitcoin, of course, and Bitcoin forks use SHA-256. Other blockchains like, Litecoin and some others use, password generation functions and that sort of thing. There's lots of different hashes that have this property of cryptographically secure pseudo-randomness. So for proof of work, we require a block, a proposed block from a miner, to have a certain number of leading 0 bits. Say, for example, we want to have 4 leading zeros in our hash. And it turns out that the higher the difficulty, the more leading zeros we have, the more guesses on average it takes for a miner to find a block. So the mechanism here is, still a little bit difficult to understand if you're new to cryptography, but also fairly simple. The more hash power you have, the higher chance you have of being the first to guess a block nonce that gives us this desired amount of leading 0 bits. Now, 4 would actually be a very low difficulty for a real blockchain. The real difficulty, values are much, much higher. So, for example, in Bitcoin, the algorithm is designed so that with all of the mining power on the network, it takes on average 10 minutes for the miners to find a block, to find the correct nonce that gives us a hash value with a certain number of leading zeros. And all of this is built on the fact that SHA-256 is a strong pseudo-random function. When you put something through SHA-256, you always get the same output, but there's no way at all to tell, based on what the input is, what the output value will look like. So if you hash hello, and you hash hello 1, you get 2 very different SHA hashes. And that's what allows this proof of work mechanism to work, is you have the block data for all the transactions in the block, sort of hashed up into the block header. And then you have miners trying to guess some random value that when appended to that and run through SHA, you get a output value that matches the difficulty requirements. Now, proof of stake also uses a mechanism that I think is very, very interesting. And I was actually learning about this fairly recently as sort of my deep dive into entropy and its use in blockchains. Proof of stake, again, uses the pseudo-random property of hashes like SHA, and they use something called a commit and reveal scheme to generate random numbers on the blockchain. So with proof of stake, instead of having miners doing a bunch of guesses, you have what are called validators. And these validators stake their coins. They say, I'm going to put up 32 Ethereum as collateral. It's sort of an honesty test that they're going to try and validate blocks that follow the rules. And if they don't follow the rules, they can have their coins slashed. So that's sort of the incentive for stakers and validators to do the right thing. Now, how do you get a bunch of validators to work together to pick one at random, right? How can we avoid gaming the system? So a validator, which it runs on a node, generates a random number from its operating system cryptographically secure source. So just like it would generate, a key to do something on a web browser, it generates a random number. And what it does is it hashes that random number and commits only the hash to the blockchain. This is the commit phase. So at the start, none of the validators know what each other's random numbers are, but they have the hash of that random number. And of course, a very important property of our Cryptosecure hash functions is that they're not reversible. So if I give you the SHA-256 hash of something, there's no way to go from that hash back to the input data without literally guessing the input data and feeding it through the hash and trying to work backwards, which is how password cracking works. Now later, all of the validators reveal their random numbers, and all of the other validators on the network can then make sure that the other nodes were honest by simply running that now public random number through the hash function and verifying that it's the same hash that was committed. So, if I generate some random number and let's say it's, 123, I put the hash on the blockchain, and later at the reveal phase, I reveal that it was 123, and all the other nodes run 123 through the hash function, and they say, okay, that matches the hash that was put in at the commit phase. And then all of the validators sort of XOR the numbers together, and they get a pooled together source of strong entropy that can be used for the validator selection. And there's further work that goes into weighting who gets picked as the validator, because the idea is you want it to be random so that anybody on the network has a chance of being picked as the validator. But you also sort of want to favor validators that are willing to put up more stake. So it's just like in proof of work, the people that put more hash power into securing the network have a higher chance of guessing. The validators that are willing to stake more of their coins, like Ethereum, will have a higher chance of being picked as the person that gets to validate the block and get the block rewards. So with this mechanism, it's impractical for nodes to game the system in their favor, since they can't easily change their number after the commit. Once they commit a hash to the blockchain, they're not going to be able to go back on their word, because all the other validators will say, if you try to come up with some other random number that gains the selection in your favor, you're not able to, change the hash. It's not practical to find a hash collision with any modern cryptosecure function. So we have a function as a question, how often does the validator RNG generation happen for every epoch? To be honest with you, I don't know the answer to that question off the top of my head. If I had to guess, this would be done for every block, but I'm not sure. So that's something I would need to look up and investigate further. That's a very good question. So thank you, Davis, for that. So in summary, it's important that we get random for this stuff. There's different types of RNGs, and the ones that we need are cryptographically secure sources. So we need to use proven systems. Use your OS's random source, right? If you're on Linux, dev/urandom, Windows has cryptgen random. Use proven systems, right? It's generally a very bad idea to roll your own crypto. And it's important, if you're developing software, to be cognizant of what random API in your programming language is cryptosecure versus the one that's not. I said earlier in the talk, the random function that most programming languages offer built in is not a cryptosecure source. Like rand in C is, I think based on Mersenne Twister. It's certainly not cryptosecure. Python's random function, random library is not cryptosecure. And there's valid use cases for those, for things like, simulations where you do want your numbers to be uniformly distributed, but also predictable for research purposes. But for crypto purposes, we need something like Python's os.urandom. So that source is one that uses the underlying OS random number generator. Random numbers are, critical for obvious things like key generation and nonces, right? Super important that we have secure keys for our private keys for crypto. But they're also critical for things like our consensus mechanisms, proof of work, proof of stake, even other consensus mechanisms that are out there use randomness in some way. Because again, we don't want people to be able to game the system in their favor and change the blockchain. It has to be hard for an attacker to start and sustain an attack on the decentralized blockchain. Getting random wrong has very serious consequences. Of course, the biggest one being coin theft and other consequences like an attacker being able to, gain control of the system through something like a 51% attack. I mean, it could be a 100% attack if, we find out that SHA or some other hash function that's used in these systems is broken. So, of course, I always like to end the talk. Anybody have any questions in the chat?
Hey Josh, that was a wonderful session. I actually got a lot many facts and figures from your talk. So yeah, that was pretty nice. See, like some like one or two questions that I had that I can actually ask you. That would be much better. So what do you think about the chain link VRF that we use? So is it reliable enough right now, or we have some considerations about that as well?
So you said Chainlink?
Yes, chain link VRF.
I have to be honest. That's kind of another question. I don't know a ton about Chainlink.
Mm-hmm.
My guess would be is, these sort of Oracle systems probably use something similar to like the proof of stake consensus mechanism, where
Mm-hmm.
they're getting a bunch of random sources from different sources on the network and putting them together in some way that an attacker can't reliably control. That would be my intuition, but I don't know exactly, how they do it.
Right, right. Yes, kind of like that. Another thing that like we were also researching about this randomness and all, is we were researching upon something VDFs, right? Verifiable delay functions. So is it like something you are supposed to solve a you can say a mathematical problem, kind of a chaining system, right? One step after the other step and so on. So it is like it won't give you you can say a feasibility that you can like get a lot of computers and solve a mathematical problem altogether and solve it in a less time, right? So it's always you're supposed to do the steps in a chain to get the final result. So I guess that VDFs can be a new consideration as well, right? What do you think about that?
So, verifiable delay functions. I feel bad. I don't know the answers to some of these questions. I haven't heard a lot about them.
Mhm.
So I would have to defer that. But
Yeah, yeah, completely fine. Yeah, we all are like researching over that, so it's like completely new area of research. And right, another question in my mind is like, as you pointed out in your talk about like ECC as well, right? Uh, Mostly being used and like proof of work, like most of the chains right now for signatures for of cryptography and all. So but we are seeing some researchers that ECC is like maybe vulnerable or like is still right now vulnerable to certain attacks. So are we looking forward to some new algorithms for these signatures? We recently saw some new cryptographic schemes and signature algorithms competing together, right? For NIST standards and so on, right? So, what are your views about that?
yeah, so the question is, what's my view? Just kind of repeating for my stream as well.
Hmm.
What's my view on, potentially replacing elliptic curves?
Hmm.
It's, I think, a fairly important consideration for future proofing blockchains. one of the questions people ask all the time is, what are major blockchains going to do about quantum computing, right?
Right.
Because elliptic curve algorithms like, the ECC, like the SecP256K1 curve, those are vulnerable to certain quantum algorithms that can break them in a much more feasible way than traditional computing can.
Mm-hmm.
So I think at some point we're going to have to replace those algorithms with something that's better. Some blockchains are experimenting with and moving towards the use of like Schnorr signatures, which my understanding is they're less vulnerable. And another fact that I find interesting is too, like with addresses, every Bitcoin address is not just a raw public key for an elliptic curve, but it's a public key hash. So we take the public key and then we run it through, for example, in Bitcoin, we run it through SHA and then we run it through RIPE MD160, which is a different hash. And so you can kind of stopgap that problem by completely avoiding address reuse. Because when you send coins, when you receive coins to your address, until you spend from that address, nobody knows your actual raw public key. So in a sense, like even if we found out a quantum computer tomorrow could break, SecP256K1, we would be able to sort of at least avoid that problems with every coin being stolen immediately, or Bitcoin just going to zero and being useless, because we have other non-quantum vulnerable algorithms standing in the way. Like hash functions aren't affected at all.
Right.
Does that answer your question?
Yes, yeah, it does. It does answers my question, and yes, actually, Davis has asking like, Josh, do you use a lot of academic paper or math proofs in your day job?
So thankfully, no. I'm going to be honest, I'm not a math guy. I mean, I did, sort of the requisite math for my computer science degree. But I'm really interested in applied cryptography. So like, I love how this stuff is applied out in the field, like in blockchains. So what I kind of like to use is I like sort of secondary sources for learning about cryptography. Like I have 2 books on my shelf over here. Practical Cryptography by Schneier and Ferguson, 2 very well-respected cryptographers, and one called Practical Cryptography,
Modern cryptography.
I think it's either Modern Cryptography or something like that. It's by J.P. Almason is a resource that I go to, and they do a really good job of breaking down sort of the general math and the general things that you need to know about crypto algorithms. So I highly recommend checking those books out as sources if you're interested in learning about this and you're not like a super in-depth math person. Because like I said, I'm not. But you can kind of learn about the general issues, which is the idea that these problems have to be hard to solve, right? We're talking about computationally difficult problems like the discrete logarithm problem and those sorts of things that make elliptic curves, and factoring large primes, right, is what is the basis behind RSA. So there's some cool other sources out there, and thanks again, Davis, for the question. There's one other question here. I don't see a name. Can the OS's random sources like dev/urandom implementations also be vulnerable to any kind of insecurities like entropy estimation, for example? At a high level, I mean, of course, they could have vulnerabilities. These systems are really, really well scrutinized. Like, for example, Fortuna, superseded an older algorithm. And one of the interesting things that I read about Fortuna is it actually does away with any kind of entropy estimation as part of the algorithm. So entropy estimation, like trying to figure out if entropy, like, say I want 8 bits of entropy, trying to figure out if that entropy is actually random is a really, really hard problem to solve, and it's really inaccurate. So modern implementations, as far as I understand, kind of do away with that. And they're really relying on what we know mathematically about the underlying crypto functions like AES in counter mode and the environmental data that we're collecting. Another thing that I think is sort of related to this is, dev/urandom will always give you random bits as much as you want. Dev/random on Linux will attempt to estimate the entropy in the pool and will block. It won't give you more bits until it thinks it's collected enough entropy to give you, like, say, another 256 bits. And from what I've read, cryptographers are kind of steering people away from that now because, again, entropy estimation is a really hard thing to do. One last thing to your point, because I want to make sure I answer your question, is, what kind of insecurities do you have to worry about? One of them that's a real practical thing that programmers and cryptographers talk about is if you have a really fresh system generating keys. So, for example, say you're a sysadmin and you're spinning up like 5 virtual machines, and they're all going to be web servers, and they're all going to start generating their own TLS certificates. There's been research done that says even though these random functions are really good, sometimes the systems on startup don't really have enough environmental entropy, like key presses and mouse movements and those sort of things, especially for virtual machine like servers and different system activity and PIDs to feed the random thing. So that's one practical consideration that folks out there can think about is, like, if you spin up a new system, you might want to, like, really hammer at the keyboard for a while or something to help feed the random sources. And that's why companies like Cloudflare even do funky things like literally filming lava lamps and using the thermal noise and the unpredictability of lava lamp movement to kind of feed their sources. Oh, yeah, and thank you, Dave. It's a serious cryptography. It's sitting on my table downstairs, and of course I'm forgetting the name when I'm talking to people. But, yeah, hope that answers the questions and everything. I think it's a really interesting topic.
It is, sir. It is. It is a really cool topic, and I would highly recommend, like, if you like a little bit of math, you should definitely be into this research because this area needs research, and this is like constantly evolving. And we need new cryptography algorithms because we want to secure our schemes from quantum computers. That is the next big risk that we will be going soon to see. But yes, and thanks to Josh for putting these research together and sharing his knowledge. And thanks for the recommendation for these books. And definitely check out these books: CS Cryptography, Modern Cryptography. These are some really cool books. And yes, so what is your next research gonna be, Josh?
I just love to tinker with this stuff. I don't go even necessarily into super deep research projects. Like, my favorite thing is just, oh, that looks interesting. Let me read about it for a while and put out a tutorial. So,
Correct.
like, I love exploring this stuff, and I always appreciate the opportunity to hopefully make computer science topics like this more digestible for people that are getting into the field and just wanting to expand their knowledge. So thanks again, everyone, for checking this out. Thanks so much to the team for having me. Again, I love the work you're doing, so much appreciated.
Yeah, thanks, Josh. Thanks for the kind words. And like, we always love the support that we got from you. Like, you're always very supportive. Like, whenever we give you a text, and you're always ready to jump in. And yeah, so that is so lovely. And like, adding to it, Josh has already did like entropy session and randomness session in the DEF CON last year, right? So we will attach that as well with this presentation, so that, like, if you're missing any step, just correlate this into like being ready for new just to move.
Cool. Well, have a great day, guys. Looking forward to the rest of the talks.
Right. Have a great day, Josh. See ya. Bye bye.